Okay, so let us cover up the remaining topics in Bohr's model. So let us start Bohr's model, calculations of radius, velocity, energy, etc. Bohr's model. Bohr's model. So the electrons are revolving around the nucleus. Nucleus has charge plus Z. We are taking hydrogen atom or hydrogen like atom. Hydrogen like atom means it has only one electron in the atom. That means it can be helium plus 1, lithium plus 2, and so on. Okay, so that's what it is. Okay, so the electron is there in some orbit, let us say, and this electron is undergoing revolution. So there is a force acting on that electron. That force we already know is electrostatic force. So the electrostatic force is giving the centripetal force, and if you take centripetal force, it is mv squared by radius. And electrostatic force is K Q1 Q2, so Z E into E. We are writing here the magnitude, right, by R square. So from here we can cancel out R, 1 R. So K Z E square by R is equal to mv square. So this is one important equation which we also got in Rutherford model also. But now the second postulate, when we are applying the second postulate, which is the angular momentum, that is the main concept here in Bohr's model. Because using the second postulate, you can solve questions, we can get the equations of quantum quantization we will get by using that second. Okay, so second postulate says that angular momentum is nh upon 2 pi. So angular momentum we know it is mvr, it is nh upon 2 pi. So from here we will be able to calculate radius. Let us calculate radius from here, nh upon 2 pi mv. So this is, let us say, equation number 2. Now we will substitute this radius in the first equation. So from equation number 2, let us substitute that. So kze square by radius. Let us substitute, and h 2 pi mv will come in the numerator, is equal to mv square. Now from here we can cancel out mass, velocity. So from here we will be able to calculate velocity. Velocity we are getting from this equation. Velocity we are getting as 2 pi k t square by h z by n. This factor we are getting. Okay. So that's the main important equation of velocity. Velocity is electron's velocity in nth orbit. Note that this is the velocity in nth orbit, so you can put Vm. Velocity of electron, velocity of electron in nth orbit. Now I want to calculate this value because all these values are already known, right? K, Z, all these things are already known. So how much this comes? It also, if you try to calculate in terms of the speed of light, comes C by 137. Okay, Z by n. Now what is C by 137? You calculate. Okay, C is the speed of light. You know that. Calculate that. Speed of light. Calculate. C by 137. You calculate. Nearly 2.19 it will come. So when you solve this, you will get this as velocity in the nth orbit as 2.19 into 10 to the power 6 factor will come, right? And this is Z by n. This is meter per second. Okay. So now you can very clearly say that the velocity of the electron is quantized. Quantized means it depends on value n. N is 1, n is 2, n is 3, n is 4. For different orbit, it is different velocity. You can clearly see that if n increases, velocity will decrease, right? Velocity is decreasing. So let's take hydrogen atom, z is equal to 1 for hydrogen atom. So if you take higher orbit, the velocity will keep on decreasing. Okay, that's the idea. Now the same thing can be now substituted in second equation to get the radius formula. So substitute this general formula here. You substitute this in radius formula and calculate radius. So radius is equal to nh by 2 pi m. V I will substitute. So V, if I substitute 2 pi k e square z by h, n comes here. So from here n square n square h square 4 pi square 4 pi square m k e square z. Okay, so finally we can say that radius of the nth orbit is proportional to n square by z. But what about the other factors? Other factors are constant, so you can write radius in terms of other factor. Other factor is nearly 0.53, right? 0.53 into n square by z, and this radius is in angstrom. We should note that the value is in angstrom. So this is the quantization of radius in Bohr's model. Hydrogen or hydrogen like atom, but also note that one important factor that I will highlight here is that it is also inversely proportional to mass. Mass is mass of electron, but in velocity mass was not coming. Note that in radius mass is coming. Okay, then next, let us go to the next. Time period also we can calculate. Now I will not do all this calculation. Time period result we will calculate. So time period of revolution. Time period of revolution. Time period, if you try to calculate time period is distance by speed in one circle. Distance is 2 pi, speed is v. So now from here try to calculate is proportional to r by v, and r is proportional to what? N square by z, and v is proportional to z by n. So from here the time period of revolution is proportional to mass. We are not taking because electron mass is same, so we have taken. So it is proportional to n cube by z square. That's the proportionality for time period. Okay. Then like that you can find out many things. I'm just giving you the idea about how do we calculate. Suppose they ask that what is the current in the nth orbit. So if they ask current current is equal to charge which is moving by time. So charge is electronic charge by time is time period. So it is inversely proportional, right? So current will be proportional to 1 by t. So time is like this way. So it is reciprocal z square by n cube. That's how current is proportional, right? Then they may ask, what about magnetic field? Magnetic they ask magnetic moment. Suppose they ask magnetic moment. So what is magnetic moment? Magnetic moment mu is equal to current into area, right? So current we know already. Now what is proportional? Area is pi r square. So mu is proportional to current, which is proportional to z square by n cube. Area is proportional to r square. Now let us substitute that. So z square by n cube, and radius was proportional to z by n. So z by n whole square. So from here you will get magnetic moment is proportional to z power 4 by n power 5, like this. So these ideas will be there which will be used in NEET exam. In NEET exam they will use these ideas, okay, these concepts. We don't have to derive, but basic things we should know We can derive within few seconds all this. Okay. Suppose they ask magnetic field. Magnetic field due to the current in the nth orbit. So magnetic field, if they ask magnetic field. So magnetic field formula, if you remember, mu naught I by 2r. So magnetic field is proportional to current and radius, right? Inversely. So already current we have calculated, radius we already know. So magnetic field is proportional to z square by n cube divided by radius is z by n. Radius is no, radius is what? I think I made mistake. Radius is n square by z. No, that's what we have to remember. This radius is n square by z. I made mistake. Radius is proportional to n square by z. So this is becoming cube. So this becomes the square of this. Okay, radius is square. So now I think this change. So magnetic moment is proportional to z square cancel, and so it is proportional to energy. Okay, it is proportional to just the quantum number. So remember, radius is proportional to n square by z. Okay, suddenly I got this. I forgot one. So n square by z. Remember this, you need to practice many times, then you remember. So B is proportional to z cube by n power 4. Like this. Okay. Magnetic moment, magnetic field, how are they related? We should remember this. I think n power 5 is coming, right? Z square z cube. N power 5 is coming. Right. Okay, so these things we have to remember. Anything they can ask, anything they can ask. Okay, so we need to remember this. That's all over Bohr's model. But in Bohr's model, very important thing is electronic transition and atomic spectra. Atomic spectra. Bohr's model. So in Bohr's model, there are all these series are there, Lyman series, constant series. But I think kinetic energy I did not. Kinetic energy we did not do. That's the most important thing. Kinetic energy plus potential energy, that is the total energy, right? Total energy. So what is kinetic energy? Kinetic energy is half mv square, right? So we can substitute value. If you see kinetic energy proportionality, this v square was there, but v is what? V is proportional to z by n, so kinetic energy is proportional to z square by n square. Similarly, potential energy, of course, it comes minus, right? Minus k z e into e by, because charge plus minus opposite, right, divided by r. So potential energy is proportional to minus z by r. Now if you see r is proportional to n square by z, so potential energy is proportional to minus z square by n square. So, and very important thing is that when you add this total energy will also become proportional to negative of z square by n square. And the total energy formula will come as minus 13.6 z square by n square, and this is in electron volt. In electron volt total energy formula. Energy is quantized. Total energy means energy in the nth orbit. Nth orbit, the energy. And also we need to note here that total energy, kinetic energy, potential energy, total energy ratio we should know. Kinetic energy, potential energy, total energy ratio. Kinetic energy 1, potential energy minus 2, total energy minus 1. This ratio we should remember. Okay, because it will help us to solve the problems fastly. Right? Go small. That's what. This is our uh, energy equation. Total energy of the orbit. We should remember that. Okay. Then what else? Then energy level diagram. I will write it. You must remember this if you want to solve question fast. Very very important. Energy level diagram. Yes. Yes, Sam. You wanted to translate. Okay. Hmm. Right. So you need to mug up all these formulas because these questions are very, very calculative. Instead of going in so much calculation, we remember these results. Okay. Okay. Yeah. Okay. Let's go to the next. Energy level diagram. Let us draw that and remember these formulas. So this is ground state and is equal to 1. It's called ground state. Ground state. N is equal to 2. It's called the first excited state. N is equal to 3. It's called second excited state. Okay, and so on, like this it will go. So let me write down the energies of this at least for 4, 5, up to 5 fifth orbit I will write, and after that you can go up to infinity, and equal to infinity also is possible. Very, very large distance from the nucleus. So let us write the energy of this first. So minus 13.6 Z square. Energy is in electron volt. Next, minus 3.4 Z square. It is in also electron volt. Next, minus 1.511 Z square. It is also an electron volt. Minus 0.85. It is also an electron volt. Minus 0.544. It is also an electron volt. Z square is also multiplied in these terms. If you take hydrogen, that means it is 1 only. Okay. So remember this, remember at least till 5. And when you take infinity, it becomes 0. Energy is 0 at the infinity. Okay. Right. So if you consider electronic transition from higher to lower, lower to higher, so that transition is due to the energy difference between them. And suppose let us consider that from some higher level to lower level, it happens, electronic transition happens from some higher level to some lower level. Okay, definitely if it is higher, it can come to here, 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 so many places it can come. Let us consider that this is higher. Higher can be anything, and this is lower, right? So when emission happens, suppose emission is happening. So photon will be released. So energy of the photon is E higher minus E lower, right? So energy of the photon is we can calculate this by taking that 13.6 common electron volt is 1 by, of course, Z square factor will come out, Z square will come out 1 by n lower square minus 1 by n higher square. This will come. Okay, and this is energy of the photon. This is energy of the photon energy. This formula, using this formula, we can calculate the photon energy, or we can calculate the wavelength, or whatever we want, we can calculate. That formula we should know. Okay, right. And this, if you want to write in joule, so note that this is 21.8. The same thing can also be written as 21.8 into 10 to the power minus 19. 10 to the power minus 19 Z square 1 by n lower square minus 1 by n higher square. This is in joule. Note that this is in electron volt and this is in joule, which is SI unit. Okay. So energy of photon can be written in terms of this in electron volt, or we can write in joule. This okay. Then what else? Okay, there is a term called wave number. Very, very important wave number, because see from here, if I use this formula, I can write energy of photon as hc by lambda. Hc by lambda. Let us write in electron volt. So, or if you want, you can use this. Anything you can use. 13.6 Z square, right? It is in electron volt to 1 by n lower square minus 1 by n higher square. Now here I will try to calculate 1 by lambda. So hc will go in the denominator here, right? Hc will go in the denominator here. 1 by n L square minus 1 by n F square. And this value when you solve, 1 by lambda, when you calculate this, 1 by lambda is called Rydberg constant. This factor will come Rydberg constant Rd, Rydberg constant. Z square 1 by n L square minus 1 by n F square. This is also called what? What it is called? Wave number. It's also called wave number. Wave number. Okay, 1 by lambda. So this Rd is here Rydberg constant. Rydberg constant. Rydberg constant. And the value of this Rydberg constant in SI unit, I am giving the values in SI unit, 1.097. 1.097. That means nearly 1 only, 10 to the power 7 per meter inverse. Okay, Rydberg Rydberg constant, we should remember that Rydberg constant. So this is in SI unit. All the calculations are in SI unit here. No need to worry about here. This is in, of course, it was here in electron volt. Otherwise, you can use this value and put it. You will get in Rydberg constant. Okay, this was electron volt. Let me put it in that. Let me put it in this form. We can substitute because this is an electron volt. Remember, so you convert this in SI unit. This is the formula in Rydberg constant. Rydberg constant. Right. Then what next? Then we need to see the emission spectra, Lyman series, Balmer series, and all that. Okay. So let us now see the atomic spectra. Emission spectra. Emission spectra of hydrogen atom. So suppose if you consider hydrogen atom, so there are various lines which is obtained. First is called Lyman series. Lyman series. What is Lyman series? That means electrons will be jumping to the ground state, n is equal to 1. Lower will be 1, higher can be anything. Anything. That means n equal to 2, n equal to 3. Electron can jump from anywhere higher. Can jump here, 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 but final will be lower only. This will be making some lines, because if it is jumping from second energy level to first energy level, a particular kind of photon will be emitted. Similarly, if it is jumping from third to first, a particular energy of photon will. Energy of photon means wavelength. Wavelength means a line. A spectral line will be generated. So those lines we are seeing in that spectrum. Okay, so we can try to calculate the wavelengths of that. So let us note those wavelengths. Okay, so we are talking of Lyman series here. So in Lyman series, the formula for 1 by lambda Rydberg constant, right? 1 by 1 square for hydrogen atom we are taken. So Z is 1 here. 1 by n higher, n higher square, because n lower is 1. This is what will be the formula. And here note that this first line First line is nothing but the transition happening from so 2 to 1. 2 to 1 transition happening. So in this case, you can calculate the maximum wavelength. Maximum wavelength when you calculate, it comes nearly 1212 angstrom. Okay. Similarly, what is the last line? First line and last line we should know. First line and last line. Last line means it is coming from infinity to 1, and in this case, the wavelength is minimum wavelength or maximum energy, that comes nearly 912 angstrom. You can substitute here and calculate. Okay, right. So this we should remember this value. Hmm. Also note that the Lyman series comes under ultraviolet region. So Lyman series is coming under UV region, ultraviolet region. Okay, and Lyman series is present in both Lyman series. Lyman series is present in both absorption and emission and emission spectra. Okay, absorption and emission spectra both. Okay, then next, let us go next. Next series we are going, that is called Balmer series, or they say Balmer. At least silent. Right. How do they pronounce it? Or what difference it makes? Idea is the same, right? So here transition is happening to lower is going to be 2, right? Not the 1. So that means transition will be happening from higher. That means from 3, that means from 4, like that transition will happen, right? 3 to 4 to 2, like that, higher to 2. So, okay, that's what it is. So here we need to note that what is the formula for the 1 by lambda, readable constant. That is readable constant 1 by 2 square minus 1 by higher. Higher can be 3, 4, 5, all those. Okay. The wavelength. Then what else? Here first line, first line means going from where? 3 to 2. Transition happening from 3 to 2. This is the maximum wavelength, which is nearly 6568 angstrom. And last line is happening from infinity to 2, so that gives minimum wavelength. That minimum wavelength is nearly 3636 angstrom. And the point to be noted here that this is going to lie in visible region. Okay, so Balmer series lie in visible region. Balmer series lie in visible region. These are questions they will ask. Which of these series line visible? Okay. Hmm. Okay. And here it is note that Balmer series is obtained only in emission. Only in emission spectrum. It is not obtained in absorption spectra, it is only obtained in emission spectra. Okay. Then next we will go to the next series, Passion series. Passion series. Passion series, what happens? The lower is 3 and higher is any other thing. So here 1 by wavelength formula, readable constant 1 by 3 square minus 1 by higher square. That means from any higher it will come to lower 3, right? So you can calculate here also the first line. First line comes as lambda maximum. Lambda maximum is 18747 angstrom. That means it is going from 4 to 3 transition happening, right? Last line, lambda minimum. Lambda minimum is 8202 angstrom, and this is happening from infinity to 3, right? Like this. And we should note important thing that Parsons rays lies in infrared, infrared, infrared region. Okay, and it is also obtained only in emission, only in emission spectra. Okay, you can note that infrared means it is a near infrared, near infrared it will be visible. Then next is what? Next is bracket. Bracket series. Bracket series, what happens? 1 by lambda is formed a Rydberg constant, 1 by 4 square minus 1 by nh square. Here, higher means it can come as 5, 6, 7 or up to infinity. Okay. So here also first line maximum lambda is coming as 40,477 angstrom. That means it is going from 5 to 4 transition. Last line lambda minimum, that comes as 14,572 angstrom. Okay, that's what it is, and this lies in uh, bracket series. Bracket series lies in infrared. Which infrared? Mid infrared region. Okay, then what else? Then last one is fund series, right? Fund series. What happens in fund series? So it is going from lower level is going to be 5, right? So 1 by lambda is Rydberg constant, 1 by 5 square minus 1 by nh square. Nh can be 6, 7 up to infinity. Okay. So here also, what is the first line? First line wavelength maximum. Maximum wavelength means corresponding to 6 to 5 transition. 6 to 5 transitions, how much it will come? 74,563 angstrom. And the last line which is infinity to 5, this last line minimum wavelength, that is nearly 22,768 angstrom. Okay. So this also lies in infrared, infrared, but this is far infrared region. Okay. So I think we have covered up this. Now, a important formula for the number of transition, total number of possible emission. Okay, total number of possible emission formula. Important formula to know: total number of possible emission, or total number of lines, spectral lines. Okay, total number of spectral lines. Suppose NH and this is NL, so electron can jump from here to here. So the total number of lines, number of spectral lines is given as nh minus nl into nh minus nl plus 1 divided by 2. That's the formula, I think. Yes. This formula we have to remember. And generally we have to take lower as 1 only, because higher will be given. From higher to lower, how many transitions are possible? Because lowest value will be ground state. So suppose electron is in the third orbit. Let us say electron is right now in the third orbit. So how many possible lines can come? Use this formula, number of spectral lines, formula. So you have to choose lower as 1. So use this formula. So 3 minus 1 into 3 minus 1 plus 1 divided by 2. So 2 get cancelled. So how much? You will get 3 only. 3 lines. How? You can now see how 3 lines will happen, because middle one is also there, which is 2. So transition can happen from 3 to 2, from 2 to 1, and from 3 to directly 1. These are the 3 lines which we can see here. 3 lines means 3 wavelengths, 3 different energy of the photons, 3 different types of photons you can see. Clear? So remember, this formula is the important formula. Okay. Hmm. Hmm. Then let us discuss the limitations of Bohr model. Limitations of Bohr model. If this Bohr model will wind up. Limitations of Bohr's model. Yes, yes. Okay. Yes, yes. What? 11th will happen next week, because right now exams are going up. Okay. Next week will start. Okay. Okay. So the first point limitation is it cannot explain. It cannot explain. It cannot explain spectra of multi-electron multi-electron atoms, because Bohr's model is only valid for single electron atom. Concept of orbit cannot be experimentally validated. Experimentally validated. Next point, it cannot explain. It cannot explain the building of atoms into molecules. That means it cannot explain any chemical reactions, why chemical reactions happen. Then principle of principle of quantization of angular momentum angular momentum, which is the second postulate, cannot be or could not be justified. Next, it violates it violates the Heisenberg uncertainty principle. Uncertainty principle. Yeah, so these five limitations we should understand. What is the first? It cannot explain the multi-electron. So Bohr's model is only limited to single electron. Single electron means we can apply the electrostatic force on single electron, and all that model we can calculate. That is right. Another thing is that if it is multi-electron means more complex interaction will happen. We cannot do anything about it. Concept of orbit cannot be experimentally validated. The concept that electrons are going in a particular orbit, that means you will be able to see electrons by microscopes or using some instruments. You should be able to find what is the position of electron from the nucleus. That means electron is right now here or here. We can never find it by any experiment till now, because the thing is that electron position cannot be visualized. It's like behaving like a wave, because such a small particle behaves like a wave. The concept of Bohr's model has failed because the wave model has come, which is Schrodinger wave model, which explains properly that probability of electron to be at a particular place. It doesn't talk about exact position, it talks about the probability of the particle to be present there. Okay, that's what it could not explain that. Okay, it cannot explain building. Of course, chemical reactions, why chemical reactions are happening, it cannot explain that. Principle of quantization. So why Bohr have kept this idea that angular momentum is quantized? He could not explain that, and it doesn't follow the uncertainty principle, because according to Heisenberg uncertainty principle, the the position as well as momentum cannot be accurately measured. If you try to measure the position of electron, you cannot measure its momentum or velocity. If you try to measure momentum, you cannot measure position. So contradiction is there, but Bohr's model is giving a definite position, a definite velocity, a definite everything definite it is giving, which itself is going against the Heisenberg uncertainty principle. That is the five important limitations of this model. Okay, then what else? Over. I think most of the things are over in this. Then what else? Done. I think we are done with this chapter. Okay. Okay, so I think we are done. Then next is about X-rays. So do you have X-rays in your NEET syllabus? What do you think? Do you have X-rays or not? Huh? X-rays is a small topic. Let us quickly finish X-rays. After finishing X-rays, after this we have finished. Okay, so no, X-rays will finish it fastly. Okay, let us go into the topic of X-rays. X-rays. We know X-ray is what? X-ray is electromagnetic wave. Let us write the theory point. Okay, theory point we need to write. X-ray, X-rays are electromagnetic wave. Okay. And how it is produced? X-rays are produced. X-rays are produced when high speed electrons are suddenly suddenly stopped suddenly stopped by a metal target. Then, okay, that's how X-rays are produced. Now, there are two types of X-rays. Let us go into the detail of continuous X-rays. Continuous X-rays. What happens is, suppose that there is a target 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 atom or target metals will be there. Some metal sheet will be there, and electrons are going with very high speed. High speed. As electrons are moving, gradually its speed will decrease because the nucleus will be there, and this nucleus will be repelling, so it will be losing energy. Loses energy, right? Because of repulsion. And because of this continuous loss of energy, it will be emitting continuously photons. So what happens is that continuous loss of energy of electrons, of high speed electrons result in high speed electron due to interaction with that. Okay, that also is there. High speed electrons due to interaction with target metal target metal atoms Continuous loss of energy of high speed electrons due to interaction with target metal atoms um, lead leads to loss of energy. No, loss already I have written. Continuous loss of energy of high speed electron due to interaction with target metal electron lead to generation of generation of photons or wave electromagnetic wave of of all possible all possible wavelengths above a above a minimum cutoff cutoff wavelength. Okay. So why minimum? Because suppose the electrons have some kinetic energy. So what happens? The loss of kinetic energy is converted as energy of photon. Okay. Whatever the energy it is going to lose, that energy will convert into photon energy. Suppose it has 100 joule. Let us take example. It has 100 joule. It can lose 20 joule. It can lose 30 joule. It can lose continuously. It can keep on losing. So whatever it is losing, that is converting into photons. So how much maximum it can lose? Maximum 100% it can lose. So if lose 100%, that converts into a photon of minimum wavelength, because you know the maximum energy means minimum wavelength, right? You know that. So if my maximum kinetic energy is lost, maximum kinetic energy lost will convert into photon, right? And maximum kinetic energy can be written as E into accelerating voltage. V is here accelerating voltage. Energy of photon is hc by lambda. Okay, so this is the minimum wavelength. So minimum wavelength we can calculate as hc by E into V. Here V is the accelerating voltage. Accelerating voltage. Okay. So the wavelength produced as continuous x-rays lambda must be greater than equal to lambda minimum. Okay. For continuous x-rays. Continuous x-rays. That is the concept of this continuous x-rays. An important property to note about continuous x-rays are continuous x-rays, continuous x-rays, continuous x-rays are independent of nature of target metal, and they depend they depend only on accelerating voltage. Accelerating voltage. Okay, and there is a very important graph here for continuous x-rays. They have given the graph for intensity, and this is wavelength in angstrom. This graph, if you see, let's see if you are keeping different accelerating voltage. For higher accelerating voltage, it go like this. Then, if you have smaller accelerating voltage, it may go like this. Then again, if you have further different accelerating voltage smaller, it may go like this. Still, if it is smaller, it may go like this. Okay. So these are different voltages. What are those voltages? I will write. This is 50 kilovolt accelerating voltage. This is 40 kilovolt. This is 30 kilovolt. This is 20 kilovolt. Okay. These are the accelerating voltage, and this value I will write -1, not -1. I think this may be 1. Okay. Some values will be there: 1 angstrom, 2 angstrom, 3 angstrom, 4 angstrom, 5 angstrom, like that. Some values will be there. Okay, 6, 7. These are in angstrom level. Okay, 8, 9, 10, like that. Okay. And note that this value lambda minimum which we have calculated can also be written as 12400 by accelerating voltage. This will come in angstrom. We can directly calculate that. Okay. So this lambda minimum is inversely proportional to accelerating voltage. Lambda minimum is proportional to 1 by V. So you can see here the lambda minimum means this point is like the minimum values. This one. For this voltage, this is minimum. 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 Okay. So for different voltages, there are minimum. For a given voltage, there is a minimum. So because we can substitute voltage and we can calculate. So this concept where minimum voltage is inversely proportional to this is called Duane and Hunt's law. Duane and Hunt's law. Okay, that's what it is. Similarly, we can also calculate frequency because this is wavelength, so frequency also can be calculated. So maximum frequency can be calculated as E into voltage by H, because this is kinetic energy, right? Into voltage is H mu, H into frequency. we can calculate this frequency, maximum frequency of emitted X-ray photons. Here you can see the intensity keep on increasing. So intensity for each of these graph, you can see there is a maximum value. After that, it decreases. Similarly, you take this graph also, there is a maximum value. From this graph, we can clearly see that there is a maximum, means there is some saturation happens. After that, it decreases. The maximum value happens. Okay. And here, how to calculate efficiency? Let us note the efficiency formula. Efficiency of X-ray tube. X-ray tube efficiency is given as percentage efficiency is output power by input power into 100. That will come as percentage. Okay, that we can calculate. Input power is V into I. Input power, remember, the input power is calculated as V into I. V is accelerating voltage, and I is anode current. Okay. Okay. Then next is characteristic wavelength or characteristics X-rays. Second type, characteristics X-rays. What are characteristics X-rays? Okay, so they are produced. They are produced due to transition of electrons from higher energy level to lower energy level in the target atoms. In the target atoms. Okay. And here it is important that the wavelength depends on wavelength of X-rays. Characteristics X-rays depends on atomic number of target element, and second thing, uh, it is independent. You can see it is independent of, so this point we can write separately. It is independent of target potential or accelerating voltage. Okay. Characteristics X-rays are made up of KLMN series of lines. We'll explain what it is. KLMN series, what it is, we'll explain. Let us see the atoms. Suppose that this is the target nucleus and we have various energy cells, right? So suppose if I say that this is First one is K, then this is L, this is M, this is N, and all that. Okay. So if electrons are trans this transition is happening to the K cell, that is called K series. Suppose if electrons are going here to here, here to here, this is called K alpha. It's called K beta. Okay. Beta means second to this K, M to K. K alpha means L to K, right? Likewise, similarly, we can have L alpha. What is L alpha, L beta? L alpha means it's coming from M to L, that is called L alpha, and if it is coming from N to L, it's called L beta. All these are photons transition happening. This is the target. Okay, remember this is target. So this is characteristics, right? Because it will depend on what is the energy of K, L, M, and of that atom, right? So according to that, this transition will give a particular kind of photons. These are X-rays, but they will have a particular energy because they are going from one particular cell to another particular cell. They give a characteristic energy. That's why it is called. It is depending on that nature of that target. Okay, right. So these things can also, if you want to see the energy, if you want to compare the energies, so let's note here the energies, comparison of energy. So I can clearly say that energy of K alpha is lesser than energy of K beta, and it is lesser than energy of K gamma. Gamma means it is coming from higher, like that. Also note one point is that energy of K alpha is lesser than energy of L alpha. That also is. Another point to be noted that intensity of X-rays, the intensities of X-rays are more for K alpha, then in this order they follow K beta, then K gamma. Okay, this is the intensity order they follow. And also note that one frequency, if you take frequency relationship, K beta is equal to frequency of K alpha plus frequency of L alpha, which will give the inverse relationship of lambda. Lambda of K beta is equal to 1 by lambda of K alpha plus 1 by lambda of L alpha. These are frequency relationship and wavelength. Why it is coming like this? Because you see, suppose if I want to take K beta, right? K beta. So K beta means M to K, it is coming, which is sum of, so energy of K beta is sum of M to L. M to L means what? M to L means what? L alpha it is. So this is energy of L alpha plus here to here this is K alpha, energy of K alpha. So now I think you can understand. We can write this as H into frequency. H will get cancelled. So that's how frequency relationship is coming, and that's how wavelength relationships are coming. Okay. These things calculations we can do anyway. Those calculations can be done anyway. That's not a big deal thing about it. Okay. Then next about here is this intensity graph. If you see in characteristics, intensity graph versus the wavelength in angstrom. So already we have discussed for continuous it will be like this. Okay, and now it will be there will be a peak. Continuous, of course, it will be going like this. But for characteristics, there will be peak like this way. Peak will be coming like this way. Okay. So these peaks represent the K alpha, K beta. So this represents K alpha and this represents K beta, right? And here we already know that this is the maximum point intensity. Let us write this as lambda naught and let us write this as lambda minimum or cutoff wavelength. So this corresponds to lambda of k beta, and this corresponds to lambda of k alpha. Now here there are some important points in this graph which we have to note. Note these important points. Okay. So as target voltage is increased, what happens we have to know. Lambda naught minus lambda minimum. This gap it decreases. This gap decreases. Then second point, k alpha remains constant. K alpha remains constant. So wavelength means k alpha means wavelength of k alpha. Because characteristics wavelength does not depend on this voltage. We have discussed already. K alpha, k beta, this wavelength will not be changed. Okay, right. But what is important to note that this difference between k alpha line and k beta line also, because k alpha remains constant, k beta also remains constant. So their difference will not change because these are characteristics. Characteristic does not change this. Okay, then what? Difference between k alpha and lambda naught. This difference, this increases. Okay, so that means lambda of k alpha minus lambda naught. This increases. This increases. Okay, that's important point. Then the last topic in this is Moseley's law. After this, it is over. The game will be over after this. The most important thing is Moseley law. Moseley's law. Okay, Moseley law. Last topic of this. So, what does Moseley law says? Moseley's law talk about the characteristics. Remember, Moseley law is about characteristics. Characteristics X-rays. They don't talk about the uh, continuous X-rays. So what they say that the square root of the frequency is proportional to target metal set, or when you remove it, it can also be written as either Z or it is proportional to Z minus. So when you remove, it will come Z minus P. Okay, like this, directly proportional to the atomic number of target. Here A and B has a special name, right? B is called screening constant, and A is proportionality constant. Proportionality constant. You can draw the graph of this also. It is possible to draw the graph of frequency, root of frequency versus Z. And if you draw this graph for K series it will come like this. So this is for K beta and this is for K alpha. And here this value of B is 1 for K series. Remember, for K series the value of the screening constant B is 1. So the slope is, even within K series the slopes are different. K alpha, K beta lines, they have different slope. Okay. So now you note here that for for K series, for K series, we should remember, if I take this ratio of frequencies, so root of frequency 1 by root of frequency 2 is going to be Z1 minus 1 by Z2 minus 1. Suppose you take two target atom and try this, you can take this ratio and do the calculations, right? That means this formula you have to apply. Okay, so that's what we need to know. What else? What about the constant A? That also you note that constant A for K gamma is greater than K beta is greater than K alpha. Values of A are different for values A, constant of proportionality. Okay. So here also note that B is going to be 1 for K series, whether it is K alpha or K beta or K gamma, this is going to be constant. What about value of B for L series? It is 7.4 for L series. This you need to remember. Okay. Also note that the wavelength uh, 1 by z, 1 by lambda can be written as Rydberg constant z minus b whole square 1 by n lower square minus 1 by n higher square. We can apply this formula of Rydberg constant for this characteristics wavelength. Note this. It looks like we are getting something from here. Okay. And one last point to be noted that this ratio lambda k alpha by lambda k beta, this ratio is nearly for a given target 32 by 27 for a given target. That means it doesn't depend on target. This ratio is constant 32 by 27 ratio. That's all. So we are done with this chapter now. So atoms is complete. Even X-rays we have completed. Then next topic is nucleus. Nucleus. Let us take in the next class, right? So we have completed this. Now you can work out any type of questions. Then next class we will take that. Right? So we'll see next class. Okay. Bye bye, Sam.